What does speed mean for China in the modern age? Throughout history, people have always wanted to travel faster. From the age of steam locomotives to today's modern bullet trains, China's rail industry keeps setting the pace and standards for rail transportation. Today, China is once again pushing beyond the physical limits of speed. China's 600 km/h high-speed Maglev system is now a reality. It has become a new symbol of China's speed, and a landmark achievement in the history of global rail development.
Testing begins now. Raise the vehicle.
Copy. Understood.
The loading sequence has begun.
Here at CRRC Qingdao Sifang today, testing is now underway on the new 600 km/h advanced high-speed Maglev train.
Good. The vehicle is now levitating steadily.
The test was successful. A train weighing dozens of tons levitated smoothly over the track. Behind that tiny gap, controlled to the millimeter, lie 5 years of painstaking work by China's dedicated railway engineers.
Beside me stands the 600 km/h high-speed Maglev train. It is currently the fastest high-speed train anywhere in the world. It fills the gap between 350 km/h high-speed rail and air travel ranging from 800 to 900 km/h. It also serves as a tool for urbanization and an engine for new quality productive forces.
On July 20, 2021, the 600 km/h Maglev, developed by CRRC Qingdao Sifang, rolled off the line. China independently developed it and owns all its intellectual property rights. It became a major technological achievement under China's national 14th five-year plan. The train represents the cutting edge of global railway technology. It demonstrates China's mastery of high-speed Maglev, from core systems to real-world engineering.
This is a whole new kind of rail system. Its defining characteristic is speed. It secures China an important strategic edge in rail transit and solidifies its leading role. Maglev also brings together innovative structures, cutting-edge technologies, and entirely new materials. It helps develop new quality productive forces and accelerates the transformation of China's entire manufacturing sector toward the higher end of the value chain. For China's goal of becoming a truly world-leading and technologically advanced manufacturing power, this system carries major strategic importance for the country's future.
Advanced high-speed Maglev technology is crucial to winning the global competition for ever greater transportation speed. It gives China a powerful transport tool to support future growth. China covers about 9.6 million square kilometers. That vast land holds tremendous potential for growth, but such immense size also creates great distances between places. With China's extensive transport network, the next challenge is to make places feel closer, reduce travel times, and connect people far more efficiently. That's the new goal China's rail engineers are now working to achieve.
China's high-speed rail now forms an 8x8 network. China's aviation network is also becoming steadily more complete and extensive. Below that, inner-city trains, subways, and urban rail systems are seeing rapid expansion nationwide. We saw a gap between air travel at 800 to 900 km/h and rail at 350 km/h. A 600 km/h system could fill that gap as an intermediate speed tier.
Advanced high-speed Maglev technology uses electromagnetic attraction to lift trains completely off the track and enable contactless travel. But developing this advanced transportation technology is extraordinarily difficult. For many years, only a small number of developed countries controlled the core technology. In 2002, Shanghai's Maglev line from Pudong Airport to downtown officially opened to passengers. It extends for 30 kilometers and tops out at 430 km/h. However, the entire line was built using German technology. By 2016, China still had not fully built its own independent, fully integrated engineering capability for high-speed maglev train systems. With foreign maglev technology tightly controlled, China urgently needed to upgrade its transportation network. So in 2016, the 600 km/h high-speed maglev project was officially launched, and this critical task fell to Ding San, CRRC's chief scientist and the project's technical leader.
After graduating from Railway College, I joined a railcar plant, unaware I would stay for nearly 40 years.
Over the course of those nearly 4 decades, Ding helped develop several of China's most important high-speed train sets, beginning with China's landmark CRH-380A train set, and continuing with the CR400AF. He helped China's high-speed rail make the leap from catching up to leading the field. But maglev was different. His extensive experience with conventional rail gave him a strong technical starting point to build on. But this was an entirely new challenge, at a completely new level of speed.
At the start, I really had mixed feelings. Many people believed the project would probably end in failure. The risks were enormous. Then I realized, this was bigger than us. It was humanity's dream, and a dream that all of us deeply shared. So we made up our minds and committed ourselves completely to the project.
Driven by the dream of pushing operating speed to the absolute limit, Ding led the 600 km/h maglev project, despite all the doubts and skepticism that surrounded him. But the first challenge came almost immediately. His first challenge was assembling a maglev R&D team.
When the team was first formed, it had very few members. Just over a dozen. To be honest, most of the original team, especially those of us in engineering, came from the conventional wheel rail, high-speed rail sector.
They were facing an entirely new kind of rail system. A small team and limited expertise were only the first major challenges. For Ding, and every single member of his engineering project team, the most difficult technical tests still lay ahead.
At this entirely new speed level, even familiar engineering problems became completely uncharted territory. No one had much experience building a system like this at full scale, for testing much less real-world use. There was no proven technical model anywhere that we could simply follow. We had to find every answer ourselves, within a completely new system. Problems once solved through practical experience and established knowledge, or standard design practice, now demanded entirely new and untested technical solutions. That made the job much harder.
There was no roadmap and no established method to follow. The team could only learn through repeated hands-on testing, carefully drawing useful lessons from every single failure along the way. And for a maglev train running at 600 km/h, the mature approach previously used for conventional high-speed rail could no longer be applied successfully.
In a maglev system, traction, operational control, and advanced signaling are integrated into one tightly connected system. Under conventional railway practice, separate teams handled rolling stock and track, and another handled line engineering. Maglev differs. Every subsystem had to be designed together and developed simultaneously within a single, unified master plan. This posed an entirely different challenge for all of us.
It required a leap into a new field. It was a tightly integrated system, with a top speed target of 600 km/h. For Ding and his entire engineering team, the difficult climb toward the world's fastest rail technology was anything but easy. To fully master maglev, every team member had to start learning from scratch and fill major knowledge gaps, master entirely new fields, and move beyond the limits of their own specialties. How could they lift the train? And once it lifted, how could they keep it stable? That became the first obstacle for the 600 km/h maglev engineering development team.
Floating a magnet is one thing, but this was a train weighing 60 or 70 tons. The first time it lifted, I was excited, but then a serious problem emerged. The train began vibrating violently.
Run the 600 km/h test cycle. Vehicle team, prepare to lower the vehicle.
Copy. Understood.
The first test fell short of expectations, leaving the team in a difficult position. There was no time to lose.
Which specific control group are these pressure switches connected to?
Deputy Chief Engineer Wu Donghua quickly regained his composure and rallied the team and pushed on, determined to make the train levitate smoothly and remain stable.
Even while traveling at a speed of 600 kilometers per hour, the train has to levitate and remain accurately aligned, with only 10 millimeters of clearance.
A 10 mm levitation gap is optimal. It delivers the best overall balance among safety, efficiency, and operating cost. It prevents guideway irregularities from making the train sway or destabilizing the levitation gap, which would drive up energy use and costs. But keeping the Maglev train operating safely, with only a narrow millimeter scale gap beneath it, is a very difficult task.
The gap sensor is one of the system's most critical components. It measures the train's precise position relative to the guideway below. It essentially functions as the train's highly accurate eyes and its highly sensitive ears. The controller functions as the system's brain. The electromagnets function like its arms and legs.
To keep the train hovering at roughly 10 millimeters above the guideway surface, the sensors must operate with extraordinary precision. For many years, this crucial core technology remained completely outside China's control. To take the initiative in this millimeter-level contest, Wu's team set out to develop its own gap sensor.
If the measured gap is even slightly inaccurate or unstable, the control system loses the basic reference it needs to operate. The sensor therefore became a top research priority. It's installed directly onto the system's main electromagnetic pole, which gradually heats up while the system is running. We therefore have to carefully examine the effects of heat on the system's electrical insulation, how it affects the accuracy and stability of the sensor readings, and whether it causes operating parameters to drift.
The sensor allows virtually no margin for error. Even a slight change in the environment can noticeably affect the accuracy of its readings. To develop a high-performance gap sensor, Wu and his team immersed themselves in test bench work. After countless tests, they finally found an accurate way to measure the electromagnet gap on a high-speed maglev train. Whatever the conditions, the sensor measures the exact distance between the train and the guideway below. Then the team faced its next major challenge. The maglev train uses a train-to-ground control system, so the question became how to transmit data from the moving train to the ground instantly, with accuracy and reliability.
The onboard wireless control unit sends each signal through the black tracking antenna on the roof. It reaches a receiver ahead of the train and is then relayed to the ground control center, establishing a train-to-ground communications link. It transmits operating commands from the ground to the train and directly controls its movement.
Under normal railway operating conditions, sending a signal is straightforward, but when the train runs at 600 kilometers per hour, it is a completely different problem.
The first major issue is the Doppler frequency shift at 600 kilometers per hour. The frequency shifts. This reflects a basic principle of modern physics. Moving objects cause frequencies to shift. You may have felt this on a 350 kilometers per hour high-speed train. At certain moments, during an ordinary phone call, the phone signal may suddenly begin cutting in and out. That signal interruption is also caused in part by the well-known physical Doppler effect.
To achieve stable, real-time wireless communication, the team had to overcome major frequency shifts, unstable signals, and the effects of changing weather.
At 600 kilometers per hour, latency must remain below 5 milliseconds, with signal jitter kept below 1 millisecond. This is an extremely tough target.
At the time, commercial wireless systems could not meet the signal transmission demands of a maglev train traveling at 600 kilometers per hour. So Wu and the engineering team returned to the lab to carefully refine the entire system, including all circuitry, key components, and the overall control strategy. They combined multiple layered technologies to combat severe signal fading, and eventually built their own train-to-ground wireless communication system. It reduced signal transmission delay to under 5 milliseconds. It became the intelligent nervous system of the high-speed Maglev, providing strong support for the Maglev train's safe operation at 600 kilometers per hour.
Then another major technical hurdle emerged. All of those controllers and precision sensors contain numerous chips that perform their essential functions. These include memory chips, high-performance FPGAs, and powerful CPU chips. So we tackled that problem ourselves and replaced them entirely with domestically produced chips. Development of all our controllers and high-precision sensors is now complete, with both already in active use on the 600 kilometers per hour high-speed Maglev train during full system testing. As a result, that major supply chain risk no longer creates delays or holds back our work.
Through sustained work, Wu's team changed the game. The critical core chips used in precision controllers and sensors could now be produced within China. That provided the 600 kilometers per hour Maglev project with a critically important boost. But at the target speed of 600 kilometers per hour, every system on the train is pushed relentlessly to its limit.
This involves far more than merely doubling the speed from 300 kilometers per hour. Although it may sound that simple, in reality the technical difficulty involved increases at a considerably faster rate. Challenges in aerodynamics, vehicle guideway interaction and control, structural strength, vibration, noise levels, and energy consumption, as well as wider environmental impact, all increase dramatically at this extraordinary operating speed.
At such extreme speeds, there is no room for approximation or imprecision. The entire train body therefore had to be designed for an entirely new category of operating speed.
Some people look at this and just see a few lines. But those lines are actually carefully shaped airflow channels. They divide and guide the air as it strikes the train. We're trying to reduce the powerful micropressure wave, while also weakening the main pressure wave itself. They weaken the upward-moving airflow as it rises toward the roof of the entire train, and allow the surrounding air to move far more smoothly across the train body.
At such a high speed, the surrounding air becomes an immensely powerful force. At 600 kilometers per hour, airflow has a greater effect on train stability, controllability, and passenger comfort than it does on conventional high-speed trains.
At this speed, the car body's pressure tightness requirement nearly doubles, from a static pressure difference of 6 or 7 kilopascals to more than 10 kilopascals. The resulting pressure fluctuations are clearly felt by passengers, especially in their ears.
For a new generation of ultra-high-speed ground transportation systems, the basic requirements are clear. They must be safe, smooth, and completely reliable, but meeting them is a major engineering challenge. Fu Shanchang has spent more than 20 years developing advanced rail transport equipment. He previously led the design of the CR400AF, a Fuxing train set designed for 350 km per hour. Drawing on deep expertise in car body design, Fu's team took a key role in developing the Maglev train.
At 600 km per hour, aerodynamic design is critical. As with modern high-speed trains, we have to reduce drag and cut aerodynamic noise. We have to manage lift. Maglev is different from wheel-rail trains. There's no contact with the track, so lift directly affects levitation control. That makes controlling lift critically important. To do that, we have to carefully shape and direct the airflow.
To achieve this, at the operating speed of 600 km per hour, Fu's engineering team reshaped the body, refined the airflow guiding structures, and tuned every key surface. But the conditions surrounding the moving train also mattered, just as much as the engineering design of the train itself.
At 600 km per hour, tunnels pose a challenge. When two high-speed trains pass in a tunnel, they generate a powerful pressure wave that strikes the car body. A Maglev faces roughly triple the pressure load of a 350 km per hour train, with peaks of about 20,000 pascals.
Inside tunnels, pressure waves created by high-speed Maglev trains can build up to extremely high levels. That makes the engineering design far more complex, and may even create serious safety risks.
At this speed, a train passing through a tunnel moves forward almost like an enormous piston compressing the air. It compresses the entire mass of air in front of it, sending strong waves outward. When these waves reach the tunnel entrance, they create a thunderous boom. At ultra-high speeds, the resulting tunnel boom becomes extremely powerful. At 350 km per hour, the pressure is about 180 pascals. With proper mitigation, it can be reduced to around 50 pascals. If poorly controlled, it can top 1000. At that level, the effects go far beyond discomfort. Hearing can be damaged, and eardrums ruptured. The danger is real. Nearby glass can also shatter.
To operate safely at these extraordinary speeds, a high-speed maglev train must be exceptionally lightweight. But that lighter train body has to survive pressure waves that increase dramatically as speed rises. This places its structural strength and airtightness under enormous stress. So Fu had to resolve a very difficult engineering trade-off. How could they make the train lighter while keeping it strong enough to withstand the pressure?
Keeping weight down is crucial. For high-speed maglev, a heavier train has more inertia. Greater inertia makes control harder. The lighter the train, the easier it is to control. At 600 km per hour, strong acceleration is essential. Our target is 1 meter per square second, 3 times that, typically achieved by conventional high-speed trains. At that acceleration, vehicle weight has a major impact on traction.
Facing strict targets, Fu's team repeatedly reviewed every technical drawing and carefully examined every single component in minute detail, over and over again. Every small detail had to be refined even further.
For the overall design, we drew extensively on proven high-speed rail aerodynamics. The concept phase began with a biomimetic approach to shaping the streamlined nose. Then we built models and put them in wind tunnels through repeated rounds of work, involving testing, adjustment, and further refinement. We reduced drag, lift, passing pressure waves, turbulence, and aerodynamic noise until all reached the train's design targets.
Fu's team carefully carried out hundreds of computer simulations and repeated design iterations. They also used advanced materials, including high-strength aluminum and carbon fiber composites, reducing the total car body weight by more than 25%. The train achieved a world-leading technical standard and gave China valuable data and experience for developing lighter rail vehicles in the future. Despite limited personnel and the vast range of disciplines to master, Ding's engineering team did not back down from the challenge of high-speed maglev. For 5 years, they tackled one difficult problem after another, without ever giving up. Ultimately, the 600 km per hour maglev system went from the drawing board to reality, showing the world how far China's advanced rail technology had progressed.
China's urbanization is speeding up rapidly. Megacities are becoming the central hubs, surrounded by many satellite cities. More people will live in and around these expanding urban centers. So this technology fits naturally with the broader direction of urban growth. That's why I believe high-speed maglev transport has strong long-term potential.
The arrival of the 600 km per hour high-speed maglev places China at the global forefront of new ultra-high-speed ground transportation technology. It's more than a technical milestone, it could become a new engine for regional development. With speeds approaching those of air travel, it can accelerate the integration of major cities. It could bring places hundreds of kilometers apart, within a 1-hour travel radius, reshaping regional economies, geography, and patterns of population movement.
This system is defined by speed, ranging from high speed to next-level ultra-high-speed travel. For our entire rail industry, it serves as a strategic tool for maintaining China's position as a global rail leader. It helps the industry continue moving from following others to leading the way. So what will be the next frontier? For the future of transport, it will be defined by much greater operating speed and by intelligent control. The advanced high-speed maglev system combines both of these major defining features.
China's rail engineers ventured beyond familiar technical ground, helping the 600 km per hour maglev advance from an ambitious vision into a working reality. It is pushing the limits of high-speed ground travel and opening a new path toward ultra-high-speed transportation. In the years ahead, this new form of transportation could reshape how humanity experiences time, distance, and urban life, while bringing China's advanced rail technology to the world.